Hi, this is Calculus 12, Chapter 6.2. We're going to be looking at integration by substitution.
This is important.
It's all about seeing patterns. So let's take a look at a simple example. Chain rule. If we're taking the derivative of u to the power of n plus 1 over n plus 1, this is u to the power of n. And we have to do du dx. So this, we take a look and put in here. So the integral of this, remember it's working backwards this way, should be this plus c. Okay, so these two are going to be equal. Must equal start. And we're just going to go through lots of different problems so that maybe you'll start seeing patterns. First example, this is what we call simple. We have the integral of x minus 3 all squared dx. So you just try something. U equals x minus 3. So find substitution. Then we take the derivative of this. Du equals dx. So we differentiate. So this equals integral of u squared du. So the clue here is substitute u and du. There should be no x's left. Okay, and there are no x's left. So now we can integrate this. This is u cubed over 3 plus c. Now we substitute it back. So we have x minus 3 cubed over 3 plus c. Let's look at something slightly harder. So there's not a lot of choices for u. U equals 3x minus 5. Du equals 3 dx. And we look and we see no 3 dx. So solve for dx. That means we have du over 3 equals dx. Now we can go ahead and substitute. We're doing the integral of square root u and 1/3 du. Okay, so we can break this apart into a fraction times du. And we integrate this. This is u 3 over 2 over 3 over 2 times 1/3 plus c. Okay, and anytime we integrate, we won't have the du anymore. And we're going to simplify this fraction. This is 2 u 3 over 2 over 9 plus c. And then we substitute back. 2 over 9, and u is 3x minus 5, and we have 3 over 2 plus c. Okay, another way to look at this, we have substitution rule. We can think of it as u equals g of x, and the integral of f of g of x, g prime of x, dx equals integral of f of u du. So to have proper algebra, we never want to substitute u without substituting du. So, for example, it's incorrect to say we're doing the integral of square root u dx. And we're trying to integrate with respect to x, but there's no x's. So don't forget to substitute the original variable back in, otherwise marks will be lost. Let's look at another medium difficulty problem. We have the integral of 1 over sine squared 3x dx, and there is no antiderivative for sine squared u. So u equals 3x. du equals 3 dx. Again, we don't have a 3 dx, so du over 3 equals dx. Now we can substitute. We're going to actually rewrite this as cosecant squared 3x dx. Now we have the integral of cosecant squared u times 1/3 du. So now we have minus cotangent u over 3 plus c. And we substitute it back in, negative cotangent 3x over 3 plus c. Okay, let's try a hard difficulty question. Now, we could try to let this be u, or let this be u. If we let this be u, we're going to have a difficulty substituting this in. So we're going to let u be cos x. du equals negative sine x dx. We have sine x dx, so we want to move the negative sign over here. So this is our combined is du. So we are integrating negative, because we have the negative here, u to the power of 6 du. And next step, we can integrate this. This is negative u to the power of 7 over 7 plus c. And now we can substitute back negative cos to the power of 7x over 7 plus c. So if we use this as u, our du would be cos x, and there's nothing we can do with this power. So our u actually has to be cos x, and you'll just see this with practice. Okay, we were doing indefinite integrals. Now we have substitution with definite integrals. When we substitute u equals g of x and du equals g prime of x dx, and we're integrating with respect to u, we have u going from g of a to g of b. So the integral from a to b of f of g of x times g prime of x dx is the integral of g of a to g of b of f of u du. So we must change the limits of integration because of the substitution. So here's a medium level problem. Solve the integral from 0 to 4 of the square root of 2x plus 1 dx. U equals g of x equals 2x plus 1. Then du equals g prime of x dx equals 2 dx. And from there, we go from 1/2 du equals dx. So g of 0, we need to change the limits of integration, equals 2 times 0 plus 1, that's 1. And g of 4 equals 2 times 4 plus 1, that's 9. Now, we can say this is I equals integral from 1 to 9, 1/2 square root u du. So let's just review here before we continue. We let u equals 2x plus 1, so we have square root u, and then we have to substitute dx with 1/2 du, so 1/2 and du. So we want to rewrite this a little bit. 1 to 9, 1/2 u to the power of 1/2 du. This is equal to 1/2 u to the power of 3 over 2 over 3 over 2. And we're integrating from 1 to 9. And this equals u to the power of 3 over 2. And the half cancels out with the half down here. So this is over 3. It's always best to simplify before we try to substitute values. And we have 9 to the power of 3 over 2. That's 27 over 3. And we have 1 to the power of 3 over 2. That's 1 over 3. So our answer is 26 over 3. Notice here, if we change our limits of integration, we don't have to substitute back. Let's look at a hard example. Integral from 0 to 4 tan x secant squared x dx. Okay, it might be hard to see where we're going for this. We could try u as being secant x, or we can have u is equal to tan x. This time, we're going to have u equals to tan x. And there's never one way of doing these. There's usually more than one way, but sometimes one way is going to be faster than another way. So du equals secant squared x dx. Okay, u of 0 equals tan 0. So that's just 0. And u of pi over 4 equals tan pi over 4. And that's just 1. Now we're integrating from 0 to 1. And since du gets substituted for all this, we just have u du. And this is not so hard. It's just seeing what we have for the substitution that's hard. And it makes it also harder when we have definite integrals. So the integral is u squared over 2, and we're integrating from 0 to 1. So we have 1/2 minus 0, so that's 1/2. Okay, this is another way. And I'm not saying that there's another way to do the substitution. There's just another way of doing the definite integral. We can solve for the indefinite integral first. Okay, and then we can substitute our original function, tan squared x over 2, substitute it back and use our original limits of integration. Generally, this is a little bit more difficult. Pi over 4 over 2 minus tan 0 is just 0, so we don't have to substitute that. And this is equal to 1, and we have 1/2. So we get the same answer, and we're going to change back to definite. And we were solving as indefinite. So when do we use this? Use if difficult to change limits of integration. Okay, let's look at another problem. A separable differential equation, dy dx. We have g of x times h of y. So we'll move the h of y over to the other side. It goes in the denominator. We move the dx over from the other side and it goes into the numerator. So now we can integrate 1 over h of y dy equals the integral of g of x dx. And we've already done this. And this is a more formal definition of what we're doing. Okay, so let's take a look at an example. Solve dy dx equals 2x times 1 plus y squared times e to the x squared. Okay, so left-hand side, we got to move all the y's over there. So dy over 1 plus y squared equals 2x e to the x squared dx. And now we integrate. We've separated. We want to integrate. So I'll just repeat that. Separate and integrate. Okay. If we look at our antiderivative tables, this is the inverse tan function of y plus c1 equals. And here we need to rewrite this e to the x squared 2x dx. This is our du. So u equals x squared. Du equals 2x dx. And now this is the integral of e to the u du. So we have e to the u plus c2. And now make explicit. Okay, explicit means solve for y. So explicit means y equals. So first step, we have inverse tan equals e to the x squared plus c. These two can be combined to make just c. Now we have to take the tan of both sides, and it's important to put plus c inside the brackets. So that's a hard problem. There's many steps to do, and just practice and you will see the patterns. And that completes this lesson.